There was a time when the Earth belonged to giants, not briefly, not experimentally, but for longer than any other large animals have ever ruled the land. For 165 to 180 million years, dinosaurs dominated nearly every terrestrial ecosystem on this planet. They endured drifting continents, rising and falling seas, ice ages and greenhouse worlds, volcanic winters and tropical extremes. They survived changes that would erase entire modern civilizations in a geological heartbeat. To put that span into perspective, modern humans, Homo sapiens, have existed for roughly 300,000 years. That means dinosaurs ruled Earth over 500 times longer than our entire species has existed. They were not a fleeting evolutionary accident. They were not a failed experiment. They were Earth's most successful large land animals, ever. And yet, they vanished. Not slowly, not gracefully, but suddenly. Picture this moment. It is 66 million years ago in what is now northwestern New Mexico. The land is warm. River systems snake through floodplains. Forests hum with insects. Herds of enormous plant-eaters move deliberately across the landscape, their footfalls shaking the ground. Among them walks Alamosaurus sanjuanensis, a titan, over 30 tons in mass, nearly 100 feet long, one of the largest animals ever to walk on land in Earth's entire history. This dinosaur is not struggling, it is not rare, it is not dying out, it is thriving. Fossils from the Nashoibito site show this ecosystem existed just 340,000 years before the end, a blink of an eye in geological time. Alamosaurus shared its world with Tyrannosaurus, Torosaurus, Hadrosaurs, Ankylosaurs, and bird-like theropods, a complete, functioning, diverse ecosystem. As paleontologist Steve Brusata put it, these dinosaurs were doing what dinosaurs had been doing for over 150 million years, adapting, diversifying, thriving. There is no sign they were in trouble. And while these animals lived, fed, nested, hunted, and migrated, utterly unaware, something else was already on its way. Far beyond the orbit of the moon, far beyond the sky they knew, a mountain-sized asteroid traveling faster than a rifle bullet. It had been moving through the solar system for millions of years. It did not speed up, it did not slow down, it did not change course. It was already inbound. In less than 1 million years, a fraction of a dinosaur lifespan, it would strike Earth with the energy of billions of nuclear bombs, excavating the Chicxulub crater beneath what is now the Yucatan Peninsula. The KPG extinction event would follow. 3/4 of all species would die. All non-avian dinosaurs would disappear. But here is the crucial truth. Nothing about dinosaur dominance hinted that this was coming. There was no warning written into their bones, no global decline etched into the fossil record, no evolutionary weakness waiting to be punished.
They were powerful.
They were diverse. They were successful. And that raises a question far larger than dinosaurs. What does dominance mean in a universe that does not warn? To understand how something so successful could vanish so completely, we must go back, not to the rise of dinosaurs, but to a world that nearly ended before they ever existed. Because the age of dinosaurs did not begin with power. It began in ruin. Travel back 252 million years.
The world you arrive in is almost unrecognizable.
This is the early Triassic, immediately following the most devastating biological catastrophe Earth has ever experienced, an extinction event so severe that it nearly sterilized the planet. The Permian to Triassic mass extinction, often called the Great Dying.
Unlike later extinctions, this one was not subtle.
90 to 96% of marine species vanished. Around 70% of terrestrial vertebrate species disappeared. Entire ecological roles were erased. Reef ecosystems collapsed. Forests vanished across vast regions. Life on Earth did not simply suffer. It almost failed. The trigger was not a single impact from space. It was something slower, crueler, and more relentless. In what is now Siberia, massive volcanic eruptions, known as the Siberian Traps, tore open the crust of the planet. For hundreds of thousands of years, lava poured out across millions of square kilometers. But the lava was only part of the damage. These eruptions released colossal quantities of carbon dioxide and methane into the atmosphere. The consequences cascaded. Global temperatures spiked. Oceans warmed and lost oxygen. Acidification dissolved shells and skeletons. Food chains collapsed from the bottom up. The seas became hostile to life. The land followed. Forests disappeared, replaced by fungal blooms, a sign of mass decay. Rivers ran through barren floodplains. Large herbivores starved. Predators followed them into extinction. For a time, Earth was dominated not by animals, but by emptiness. This was not a world ready for giants. It was a world stripped to its foundations, and yet, life persisted. A few lineages survived, and not because they were stronger, faster, or smarter, but because they were flexible. This period introduces one of evolution's most important principles: survival over superiority. The survivors of the Great Dying were often small, generalist, opportunistic, and able to tolerate heat, low oxygen, and instability. Complex ecosystems did not return quickly. For millions of years, Earth existed in a biological holding pattern. This is known as an evolutionary bottleneck, when only a narrow slice of life makes it through, and everything that comes after must be built from those survivors. The planet itself was wounded. Climate swung wildly. Oxygen levels fluctuated. Soils were poor. Food webs were fragile. There were no dinosaurs here, no Tyrannosaurus, no Triceratops, no long-necked giants, only scattered survivors, early amphibians, primitive reptiles, and small archosaurs, cautiously expanding into an empty world. This emptiness is critical, because mass extinctions do not simply destroy life, they create opportunity. Ecological niches, once occupied, now stood vacant. Predators were gone, herbivores were gone. Entire modes of living had vanished. The rules of the game had been reset. And in this unstable, dangerous, half-dead world, evolution began experimenting again, slowly, clumsily, with no guarantee of success. Some lineages would rise, only to fall. Others would dominate briefly, then disappear. The future rulers of Earth were not yet obvious and not yet impressive. But somewhere in this chaos, new predators were already evolving, watching, waiting, learning how to survive in a broken world. The world had not yet learned the shape of a dinosaur. It is roughly 240 million years ago, deep in the late Triassic, and the land is already dangerous. Not empty anymore, not quiet, but crowded with predators that have learned how to rule a wounded planet. The air is warm, the seasons extreme. Rivers cut through red floodplains. Forests rise and collapse with the climate's mood. Life is rebuilding itself after near annihilation, but it is doing so unevenly, experimentally, and without mercy. The dominant animals on land are not dinosaurs. They are pseudosuchians, members of the crocodile line of archosaurs. The name means false crocodiles, but that is deeply misleading. These creatures are not slow, semi-aquatic ambushers. They are tall, fast, armored, terrestrial predators and herbivores, occupying nearly every major ecological role that dinosaurs will later inherit. In this world, the crocodile lineage is not lurking at the edges of rivers. It is in charge. Some pseudosuchians walk upright on pillar-like legs. Others move with a high walk posture that lifts the body off the ground, allowing efficient, sustained movement. Many are covered in osteoderms, bony armor plates embedded in the skin, forming protective shields along their backs, flanks, and tails. These animals are built for combat, endurance, and dominance. Among them stalks a predator recently brought to light by science, one that, until very recently, we did not know existed. In southern Brazil, within rocks dating to around 240 million years ago, paleontologists uncovered the remains of a medium-sized carnivore. It was roughly 8 feet long, powerfully built, and clearly an active hunter. Its bones told a story of speed, strength, and predatory intent. The animal was named Tyrannosaurus bellator. The name translates roughly to fierce crocodile warrior, and it is an apt description. Described in 2025 in the Journal of Systematic Paleontology by Dr. Rodrigo Temp Müller and colleagues, Tyrannosaurus belongs firmly to the Pseudotsuchian lineage, yet at first glance it looks unsettlingly like a dinosaur. It has a lightly built skull suited for slicing flesh. Its limb proportions suggest an agile terrestrial hunter, rather than a swamp-dwelling ambush predator. Its body posture indicates it carried itself high off the ground, not sprawled. Its osteoderms provided armor without sacrificing mobility. This resemblance is not accidental. It reveals something deeply important about evolution. Tyrannosaurus did not copy dinosaurs. Dinosaurs had not yet arrived. Instead, both lineages were responding to the same pressures: open ecological niches, unstable climates, and fierce competition in a recovering world. Evolution was experimenting with similar solutions in different branches of the Archosaur family tree. Dr. Müller noted that animals like Tyrannosaurus show how misleading appearances can be in deep time. As he and his colleagues emphasized, these predators demonstrate that many of the traits we associate with dinosaurs evolved earlier and independently in other archosaurs. The difference lies beneath the surface, in the bones that control motion. Dinosaurs possess a distinctive pelvic and femoral anatomy. Their hip socket is open, allowing the femur to swing directly beneath the body in a fully erect stance. This configuration enables efficient locomotion, longer strides, and sustained activity over long distances. Pseudotsuchians like Tyrannosaurus, by contrast, retain a different articulation of the hip and thigh. Though capable of upright movement, their anatomy reflects a separate evolutionary pathway, one that favors power, armor, and versatility rather than the extreme efficiency that will later define dinosaurs. To the untrained eye, the two can look nearly identical. To evolution, they are rivals. At this point in Earth's history, the rivals are winning. Across Pangaea, the vast supercontinent that still binds South America and Africa together, Pseudotsuchians dominate. Their fossils appear on both sides of the Atlantic because the Atlantic does not yet exist. Animals move freely across what will someday be oceans. This geographic connection matters. The discovery of Tyrannosaurus reinforces how interconnected Triassic ecosystems were. South America and Africa shared predators, prey, and evolutionary experiments. This was a single biological theater, stretching from pole to pole, where archosaurs diversified explosively. Dinosaurs, by comparison, are present only as minor players, small, rare, ecologically insignificant. They appear in the fossil record as lightly built bipeds, more prey than predator. They do not dominate food webs. They do not control landscapes. They are one lineage among many, overshadowed by larger, better-armed, better-established competitors. This is a crucial correction to the popular image of dinosaur inevitability. Dinosaurs did not rise because they were destined to. They rose because others fell. And at this moment in time, there is no sign that the crocodile line is about to relinquish control. Pseudotsuchians include not only predators like Tyrannosaurus, but also massive herbivores, apex carnivores like Rauisuchians, and semi-aquatic hunters like phytosaurs. They fill the rivers, the floodplains, and the forests. They are evolution's current answer to dominance. Dinosaurs are simply waiting. This period reveals a deeper truth about how power works in natural history. Dominance is not invented, it is inherited. When one lineage rules, it does so atop the ruins of another. The Triassic world was already shaped by extinction, and now it was governed by survivors who had seized the opportunity first. As paleontologists have increasingly emphasized, dinosaurs were not superior in every respect. Many Pseudotsuchians were larger, more heavily armored, and equally capable predators. For tens of millions of years, they held the advantage. What ultimately changed was not intelligence or strength. It was contingency, volcanic pulses, climate shifts, environmental instability. The same restless Earth that had nearly ended life once before was still unstable beneath their feet. The late Triassic world is therefore a lesson in humility. Even the rulers of Earth live on borrowed time. Tyrannosaurus bellator hunted, fed, and survived in a world where dinosaurs were evolutionary background noise. Its kind-shaped ecosystems controlled prey populations and enforced the hierarchy of the land. Yet its lineage would not survive the next great transition, and the dinosaurs it overshadowed would, not because they were stronger in this moment, but because somewhere, quietly, a different lineage was learning to run. The first dinosaurs did not arrive with a roar. They did not strut across continents as kings of the land. They appeared quietly, almost timidly, in the shadows of a world still ruled by the Pseudoseuchians, the crocodile-line archosaurs that had inherited the Earth's chaotic post-extinction landscape. It is roughly 245 to 230 million years ago, in the late Triassic, and life is still recovering from the devastating Permian-Triassic extinction. Ecosystems are fragile, rivers shift unpredictably, and forests spring up only to be burned or flooded. Amid this fragile, dangerous world, the first true dinosaurs emerge, small, fast, and largely unnoticed. These animals were remarkable, but not in the ways the public imagines. There are no towering sauropods yet. There are no Tyrannosaurus-like predators. Instead, there are creatures like Herrerasaurus, Eoraptor, and Coelophysis. Herrerasaurus, discovered in Argentina, measures roughly 10 to 20 feet in length, light-boned and bipedal, built for speed rather than brute force. Eoraptor, even smaller, is little more than a swift two-legged predator or omnivore, darting through undergrowth, seizing insects. Coelophysis, one of the more common late Triassic forms, is sleek, elongated and delicate, a skeleton designed for efficiency, not intimidation. What set these early dinosaurs apart from their Pseudoseuchian neighbors was not their size or ferocity. It was their skeletons, subtle differences encoded in bone and muscle that would, millions of years later, allow them to dominate nearly every terrestrial ecosystem. The hallmark is the open acetabulum, the hip socket that distinguishes Dinosauria. This open, bowl-shaped joint allows the femur to swing directly beneath the body, an innovation that enables an upright posture. With legs tucked under rather than sprawling to the sides, these animals could move with unprecedented efficiency. They could run faster, sustain locomotion over greater distances, and maneuver agilely in dense forests or open floodplains. The stride of a Herrerasaurus or an Eoraptor is not just a mechanical detail, it is an evolutionary promise. With this posture, dinosaurs are freed from some of the constraints that limit Pseudoseuchians, whose semi-sprawling gait, though powerful, is less energy efficient for sustained movement. The dinosaurs of the late Triassic are like fledgling engineers of motion, experimenting with biomechanics that will eventually allow some lineages to grow enormous or pursue prey with coordinated precision. The fossil evidence reveals more than just bones. Trackways discovered in Argentina and other parts of Gondwana indicate that even these small dinosaurs may have hunted or moved in loose social groups. They were not apex predators, they were survivors. They occupied niches ignored or inaccessible to larger Pseudoseuchians, dense forests, uplands, and open plains where speed and agility were more advantageous than size or armor. Their diets were equally flexible. Some were carnivorous, some omnivorous, others likely opportunistic feeders that could exploit insects, small vertebrates, and plant matter, adapting to whatever resources the fragile ecosystem could provide. Scientists studying these early dinosaurs emphasize that their significance lies not in their present power, but in their evolutionary potential. As paleontologist Steve L. Brusata has noted in Modern Analyses, Herrerasaurus and Eoraptor are not impressive as individuals, but their bodies carry the blueprint of an entirely new way of being. Upright, bipedal, active. These traits will allow their descendants to experiment with forms that we can barely imagine. These animals are, in essence, the underdogs of deep time. They are not yet kings, but they carry the genetic and anatomical seeds of future dominance. The environment in which these first dinosaurs appear is unstable. Volcanism is frequent, shifting climates are common, and sea levels fluctuate. The late Triassic is a period of transition, with continents still fused into Pangaea but already beginning to fracture. This fragmentation isolates populations, creating opportunities for divergence, adaptation, and experimentation. In these isolated pockets, early dinosaurs quietly explore new ecological strategies, while their Pseudoseuchian neighbors continue to dominate the landscape with brute strength and armored intimidation. Even more striking is that the first dinosaurs arrive after a world-shaping extinction, and yet they are not immediately victorious. The lessons of the Permian-Triassic extinction have not been forgotten. Survival is still paramount. These animals must navigate predators far larger than themselves, avoid environmental hazards, and compete for food in a patchy, uncertain landscape. Every small advantage counts. The open acetabulum, the upright stance, the lightweight skeleton. All these features are subtle weapons that allow these early dinosaurs to persist. They survive not because they are the strongest, but because they are adaptable, efficient, and resilient. Paleontologists like John R. Horner and Kevin Padian have emphasized that the first dinosaurs should not be viewed through a lens of later grandeur. Their power lies in potential, not present dominance. Chelophysis, for instance, may have hunted in groups, using coordination and strategy rather than size to overcome prey. Eoraptor's modest teeth suggest a flexible diet that could withstand ecological fluctuations. Herrerasaurus, though larger, still faced competition from top-tier pseudosuchians. Each step, each survival, is a small experiment in evolutionary ingenuity. The fossil record also hints at the social behaviors and life strategies that will become important later. Egg clutches from slightly later Triassic sites show that these small dinosaurs, like their descendants, were likely site-faithful nesters, returning repeatedly to the same safe grounds for reproduction. Juveniles grew rapidly, evidenced by growth rings in bones, a pattern suggesting high juvenile mortality, but also remarkable capacity for population recovery. These life history strategies, though subtle, foreshadow the herding, nesting, and migratory behaviors that will define the age of dinosaurs in the Jurassic and Cretaceous. It is crucial to understand that the world of 245 to 230 million years ago is still experimenting with life. Dinosaurs are a minor footnote at first. The real rulers are pseudosuchians, giant herbivores and apex predators that dwarf these small bipeds. Yet the first dinosaurs are quietly learning to occupy space, to optimize energy, to exploit niches invisible to larger competitors. Evolution does not rush. It does not announce itself. It works in the margins, in the overlooked, the underestimated, the small and fast creatures that survive when giants fall. And fall they will. The Triassic world is not static. Within a few million years, Earth will shake again. The forces that have shaped life so violently before, massive volcanism, fluctuating climate, and ecological stress, will return. This time, the consequences will be dramatic, wiping out the dominant pseudosuchians and clearing ecological space for dinosaurs to rise. The first dinosaurs, the small, fast, and seemingly forgettable creatures, will inherit the opportunities carved by catastrophe. Their evolutionary experiments, begun in the shadows, will suddenly become the blueprint for dominance across the Mesozoic. For now, though, they are survivors in a world that does not yet recognize them. They run, hunt, forage, and breed under the threat of larger predators. They occupy the margins, the narrow corridors of ecological possibility. And yet, with every step, every successful hunt, every fledgling reaching adulthood, they are quietly reshaping the future of terrestrial life. In the evolutionary story, the first dinosaurs teach a lesson. Greatness often begins in obscurity, in the small, the agile, the underestimated. They are not kings yet. They are experiments in motion, biology testing the limits of possibility. And then, the world burns again. Soon, the late Triassic extinction pulse will strike, reshaping the balance of life. Many of the pseudosuchians that now dominate will vanish. Some early dinosaurs may vanish too, victims of the same catastrophe. They will ultimately survive through adaptation. But the survivors, the agile, the fast, the biologically prepared, will step into an emptied stage and begin a journey that will last over 160 million years, culminating in giants like Alamosaurus and fearsome hunters like Tyrannosaurus rex. This is the story of resilience, of latent potential, of life quietly biding its time until opportunity arrives. It is the story of evolution's patient, meticulous, and often unpredictable artistry. If you want to continue following the rise of these remarkable creatures, from small, overlooked bipeds to colossal rulers of the Mesozoic, subscribe and stay with us. The journey has only just begun. The world of 209 million years ago was a tapestry of rivers, forests, and volcanic ash, a landscape both lush and perilous. In what is now northern Arizona, along the meandering streams and floodplains of the late Triassic, life thrived in ways that would surprise anyone expecting dinosaurs to dominate every corner of the land. Here, in the sediments that would become the Petrified Forest National Park, a remarkable story is captured in stone, a story of thriving ecosystems without the colossal footprints, the thunderous herds, or the razor-toothed hunters we now associate with the age of dinosaurs. The fossil record in Arizona preserves an ecosystem that was diverse, complex, and in many ways unfamiliar. Researchers, led by Dr. Ben Kligman of the Smithsonian National Museum of Natural History, catalogued 16 vertebrate species, 7 of which were entirely new to science. What stands out immediately is the absence of true dinosaurs. The landscape is populated by crocodile-line archosaurs, armored herbivores, and amphibians. Predators loom large, yet they are not the bipedal, upright hunters that would later captivate our imagination. Dinosaurs are either completely absent or exist only in marginal numbers, as quiet, unremarkable presences. In this world, dominance belongs to other lineages. The preservation of this ecosystem is extraordinary. Volcanic ash blankets the floodplains, burying creatures almost instantly and creating the conditions for exquisitely detailed fossilization. Limbs, skulls, and teeth remain articulated, offering scientists a snapshot of life as it existed millions of years before dinosaurs would become the kings of the land. This is not a dying ecosystem, nor is it an impoverished one. Amphibians hop through undergrowth, freshwater sharks patrol rivers, early turtles crawl along muddy banks, and armored herbivores graze cautiously. Pseudosuchians, some more than 6 meters long, patrol the top of the food chain, demonstrating that power, for now, belongs to those who came before. The environment itself was tropical and equatorial, sitting near the heart of Pangaea, when the supercontinent had not yet fragmented into the continents we know today. Seasonal rains swelled rivers, creating fertile floodplains, while occasional droughts stressed the smaller species and triggered migratory behavior. Volcanic activity was frequent, and ash-laden eruptions reshaped landscapes suddenly and violently, killing some populations while providing rich sediment for new life to take root. These cycles of destruction and regeneration created niches for both aquatic and terrestrial life to exploit, but they also placed constraints on the growth of early dinosaurs who were still small and relatively fragile. The dominant predators of this ecosystem were formidable. Crocodilomorphs and Rauisuchians patrolled the rivers and forests with a combination of power, speed, and lethal precision. Fossilized teeth and skeletal reconstructions show muscular, high-reaching jaws, long limbs built for bursts of speed, and osteoderms, bony plates embedded in the skin that served as both armor and signaling structures. These were not passive hunters, they were apex predators capable of striking fear into any smaller vertebrate that crossed their path. Dinosaurs, by contrast, were more like understudies in this drama, waiting, learning, and evolving in the periphery. Among the most intriguing discoveries in Arizona is a small early pterosaur named Eotephrodactylus mcintyriae, one of the oldest flying reptiles known from North America. With a wingspan of roughly 1 meter, delicate skull bones and curved teeth adapted to catching fish, it demonstrates that vertebrates were already experimenting with flight tens of millions of years before the first birds would appear. Eotephrodactylus is an evolutionary pioneer, exploiting a niche that no terrestrial predator could reach. Its presence underscores a central truth of life in the Triassic. Success does not require dominance on the ground. Sometimes the future belongs to those who take to the air, who move into unexplored spaces, who adapt to opportunities invisible to larger competitors. The Arizona fossil beds also preserve evidence of intricate ecological interactions. Herbivorous reptiles feed along riverbanks, sometimes partially armored, suggesting selective predation pressures. Early amphibians move in and out of water, showing complex life cycles dependent on seasonal patterns. Fish, including early freshwater sharks, swim in the rivers, providing sustenance for both reptiles and pterosaurs. Each species, each interaction, reflects a finely tuned web of life that has not yet been disrupted by the rise of dinosaurs. In this ecosystem, power is exercised not through size alone, but through specialization, strategy, and adaptability. Dr. Kligman, in his PNAS publication, emphasizes the importance of this site for understanding the nature of early Mesozoic life. He notes, "The petrified forest preserves a world in which dinosaurs were not inevitable rulers. They existed, but only on the margins. The dominant roles were filled by lineages that would soon vanish, swept away by extinction pulses that were still to come." It reminds us that ecological supremacy is never permanent. It is contingent, fragile, and subject to forces far larger than any individual species. This reflection is crucial because it reframes the story of dinosaurs. Their eventual dominance, so often imagined as inevitable, was in fact the result of historical contingency, catastrophic extinction events, and millions of years of subtle evolutionary experimentation. For the first time, the Arizona record allows us to see dinosaurs as underdogs. Their small size, upright gait, and evolutionary innovations place them on the sidelines, quietly learning the mechanics of locomotion, diet, and social behavior, while larger competitors patrol the forests and rivers. Every predator-prey interaction, every foraging strategy, every survival is a rehearsal for the future, a series of experiments in adaptation that will pay dividends only after cataclysm reshapes the ecological stage. The broader lesson of the petrified forest is that the rise of dinosaurs was not a foregone conclusion. In this lush, volcanic, equatorial world, other lineages had already solved the problems of predation, defense, and reproduction. Dinosaurs were not yet kings, nor even particularly remarkable. They were small, swift, and largely inconspicuous, yet they carried with them the structural innovations and behavioral plasticity that would later allow them to fill the ecological void left by mass extinction. The open acetabulum, parasagittal gait, and rapid growth rates that had proven advantageous in marginal niches would soon become the foundation for the spectacular diversity of the Jurassic and Cretaceous. And then, in the midst of this ground-bound world of rivers and predators, the first creatures capable of sustained flight appear. Eotiphrodactylus and its kin demonstrate that evolutionary potential can emerge in unexpected directions, beyond brute strength and territorial dominance. The skies, until now largely empty, offer a new frontier. Dinosaurs may eventually rise to rule the land, but the air has already been claimed by a small, agile, and remarkable lineage that hints at the creative unpredictability of evolution.
Arizona reminds us that history is not linear, that dominance is provisional, and that the world we imagine as natural is always contingent on chance, extinction, and innovation. The first dinosaurs survive quietly, observing, adapting, and preparing for a future in which the rules will change entirely. They are not kings yet, but they are learning the lessons of endurance, efficiency, and flexibility that will carry them across millions of years. And in the shadows of these tropical rivers, under the watchful eyes of predators far larger and more powerful than themselves, something remarkable is quietly unfolding. Evolution is experimenting, pushing the boundaries of form and function, setting the stage for the creatures that will one day dominate every forest, floodplain, and desert on the supercontinent. The first dinosaurs are still learning to run, still learning to survive. And somewhere above, the first wings beat against the air, hinting at a future in which life will conquer not only land, but the skies themselves.
In the twilight of the late Triassic, long before dinosaurs would rule the land, the skies began to host a drama all their own. Among the volcanic ash and river sediments of what would become northern Arizona, a delicate creature spread its wings and took to the air. Its name, Eotephrodactylus mcintiri, evokes both myth and science, the ash-winged dawn goddess, and its discovery tells a story of evolution, reaching beyond the constraints of gravity, of life experimenting in directions the ground-bound giants could not imagine. Eotephrodactylus was small by modern standards, with a wingspan barely reaching a meter, yet its anatomy reveals a creature exquisitely adapted to its environment. Unlike the dinosaurs scrambling across floodplains below, it could rise above, seizing fish from the rivers with curved front teeth and slicing through its prey with blade-like rear teeth. Its elongated fingers supported a wing membrane, while a long tail, a primitive trait lost in later pterosaurs, helped stabilize it in flight. The fossilized remains, preserved in fine volcanic ash, offer a remarkable window into the earliest days of vertebrate-powered flight in North America. This was a time when the skies, until then empty of vertebrate predators, suddenly became a domain of life's relentless ingenuity. The significance of Eotephrodactylus extends beyond its size or diet. It represents the first major leap in evolutionary experimentation, the conquest of air, something no terrestrial predator could do. As Dr. Ben Kligman notes, the appearance of powered flight marks a turning point in vertebrate evolution. It's a profound innovation, one that would forever change the ways in which life interacts with its environment. While dinosaurs were still learning to walk efficiently, these early pterosaurs were mastering lift, drag, and maneuverability, opening a realm of possibilities inaccessible to their land-bound cousins. The volcanic ash that entombed Eotephrodactylus also preserved the broader ecosystem. Tropical rivers teeming with fish, early turtles crawling along the banks, amphibians leaping from mud to water, and armored herbivores grazing cautiously. It was a dynamic, fully functional ecosystem, yet the dinosaurs were conspicuously minor players, quiet observers in a world dominated by other reptiles. The evolution of flight was a signal that innovation often comes from the margins, from the creatures underestimated or overlooked, and that the future is rarely shaped by those who appear strongest today. Eotephrodactylus also embodies the way science remembers its contributors. The species name honors Suzanne McIntyre, whose meticulous fieldwork and dedication ensured that this delicate fossil was excavated, studied, and contextualized. It is a reminder that each fossil carries not just the story of the creature itself, but of the people who devote their lives to uncovering fragments of deep time. This small pterosaur, preserved in volcanic ash, becomes a symbol both of evolutionary daring and of human curiosity, bridging hundreds of millions of years in a single, fragile skeleton. In its flight, Eotephrodactylus demonstrates that survival is not only about size, strength, or domination. It's about exploiting opportunities, innovating in unexpected ways, and occupying niches that remain unclaimed. While dinosaurs would eventually evolve into giants, predators, and complex social organisms, for now, it is the air that hosts the daring experiment, the first taste of true vertebrate freedom. Yet, even as these small pioneers mastered the sky, the land beneath them was in turmoil. The Triassic world was precarious, a stage set for mass extinction. Volcanism was intensifying in regions such as the Siberian Traps, releasing enormous volumes of carbon dioxide and other gases into the atmosphere. Oceans teetered on the edge of anoxia, rivers fluctuated between flood and drought, and the delicate equilibrium of terrestrial ecosystems was under threat. Extinction was sharpening its blade, a force indifferent to innovation, size, or ambition. No creature, however swift, armored, or winged, could escape the planetary scale forces that would soon rearrange life itself. For the dinosaurs, this was a time of patience and preparation. Small, fast, and relatively inconspicuous, they observed, adapted, and persisted on the margins of these early ecosystems. Their innovations, upright posture, open acetabulum, parasagittal gait, were subtle yet profound. These anatomical features allowed them to exploit spaces and resources that the larger, dominant pseudoseuchians could not. Every step, every adaptation, was a rehearsal for survival in a world where extinction would redraw the rules, abruptly and without warning. Meanwhile, the skies had already been claimed by the first true vertebrate flyers. Eotephrodactylus and its kin foreshadowed a world in which life could escape the constraints of the ground, explore new feeding strategies, and colonize habitats unreachable by terrestrial predators. Flight was a radical innovation, a demonstration that evolution can solve problems in ways no single lineage can anticipate. And yet, even these pioneers were not immune to extinction pressures. Triassic volcanism, climate instability, and the shifting mosaic of ecosystems ensured that only the adaptable would endure. The fossil record of Eotephrodactylus mcintiri is a testament to the dual nature of evolution, creativity and fragility. It reminds us that dominance is temporary, that life's experiments are often marginal, and that innovation is often punished as well as rewarded. The dinosaurs, still relegated to the edges of the ecosystem, were observers of this experiment, learning, evolving, and waiting for the moment when the stage would shift irrevocably in their favor. In this world, survival was not a matter of immediate triumph, but of resilience, flexibility, and preparation. On land, the dominant pseudosuchians and other reptiles held sway, but the groundwork was being laid for the eventual rise of the dinosaurs. Flight for Eotephrodactylus was the cutting edge of evolution, an early signal that life constantly seeks new solutions, new territories, and new ways to persist. The earth below was teeming with competition, yet the skies had already been claimed, showing that evolution is multidimensional, opportunistic, and often unpredictable. The story of Eotephrodactylus is a story of ingenuity in miniature, a reminder that the future belongs not only to those who are powerful today, but also to those who innovate, explore, and survive in unexpected ways. Dinosaurs, for now, are still sidelined, but the lessons of flight, of ecological experimentation, and of adaptation are quietly imprinting themselves on their evolution. And while the air opens new possibilities, the land waits, tense and uncertain, for extinction to carve the path that will make room for the rulers of the Mesozoic to emerge. And so, even as the first wings beat against the equatorial skies, the earth beneath is primed for upheaval. Extinction pressures intensify, reshaping the balance of life in ways that will favor those most adaptable, most efficient, and most ready to seize opportunity when it arrives. The dinosaurs, though small and unremarkable, are poised to inherit the stage once catastrophe clears the playing field. The skies may have opened first, but the land will not remain forever unconquered. The epoch of innovation and survival is far from over. Life is experimenting, pushing boundaries, and waiting for the moment when the dice of extinction fall in favor of a new generation of rulers. Eotephrodactylus shows that evolution is daring, the skies are a frontier, and even the smallest innovations can herald a new era. But on land, forces are gathering, pressures mounting, and extinction is sharpening its blade, ready to sweep away those unable to adapt. The world that had been meticulously constructed over tens of millions of years, a mosaic of rivers, forests, deserts, and skies teeming with life, was suddenly undone. Around 201 million years ago, the delicate balance of the late Triassic shattered. Massive fissures opened in what would become the Central Atlantic, spewing rivers of molten rock that would later be recognized as the Central Atlantic Magmatic Province, CAMP. This vast volcanic episode released unimaginable volumes of carbon dioxide and sulfur gases into the atmosphere, heating the planet, acidifying the oceans, and destabilizing ecosystems on a global scale. It was the end Triassic mass extinction, one of the 5 great extinction events of Earth's deep history, a planetary reset that would forever alter the trajectory of life. The eruption of CAMP was not a quiet affair. Basalt flows covered millions of square kilometers, lava rivers spilling into lowlands and forests alike. Atmospheric carbon dioxide levels surged, triggering a rapid greenhouse effect. Temperatures rose sharply, and the combination of acid rain, global warming, and widespread forest fires stressed terrestrial ecosystems to the breaking point. The oceans, already shallow and warm, suffered from anoxia, zones where oxygen levels dropped catastrophically. Fish, amphibians, and marine reptiles suffocated in waters that had once been hospitable. On land, the dominant reptiles, the Rauisuchians, giant 4-legged predators reaching 6 meters or more, and the crocodile-like phytosaurs, found their territories collapsing, their prey disappearing, their physiological tolerances pushed beyond survival. The impact on life was devastating. Fossil evidence shows a dramatic turnover. Entire lineages vanish with no trace beyond the Triassic layers. Rauisuchians, which had been apex predators for tens of millions of years, disappeared entirely. Phytosaurs, semi-aquatic hunters with nostrils perched atop their snouts, likewise vanished. Other reptiles that had dominated the late Triassic floodplains, from armored herbivores to small carnivores, were drastically reduced or gone. It was an era of planetary-scale culling, where dominance mattered little and survival hinged on resilience, flexibility, and a capacity to endure environmental volatility. Yet amidst this catastrophic upheaval, certain lineages persisted. Frogs, small and adaptable amphibians, survived likely due to their burrowing behavior, ability to exploit small water bodies, and life cycles that could tolerate drought and temperature swings. Turtles, with their protective shells and slow metabolism, weathered the environmental stress. Pterosaurs, light, mobile, and able to exploit aerial niches, navigated the collapsing terrestrial ecosystems with relative advantage. And the dinosaurs, still small, unassuming, and often marginal in the late Triassic, endured. Their success was not a product of strength or dominance, but of adaptability. Upright posture, parasagittal gait, efficient metabolism, and generalist feeding strategies allowed them to navigate the chaos. Their small size made them less vulnerable to resource scarcity. Their mobility enabled them to escape environmental hotspots, and their reproductive strategies, including high egg-laying rates and nesting in protected sites, ensured that at least some offspring survived. This extinction, in effect, created an ecological vacuum. The ruling reptiles of the Triassic were gone, leaving niches unoccupied and ecosystems destabilized. Dinosaurs, once marginal, suddenly found themselves in a world with far fewer competitors. There were no giant rauisuchians to dominate the floodplains, no phytosaurs to control the river systems. Forests regrew in gaps cleared by fires, insects proliferated in abandoned habitats, and herbivorous niches remained largely unclaimed. Dinosaurs, with their upright stance and efficient locomotion, were poised to exploit every available opportunity. Nature did not reward aggression or size here. It rewarded persistence and versatility. The mechanics of this extinction reveal a sobering reality. Volcanism altered the chemistry of both air and water. Sulfur dioxide from the lava flows likely led to acid rain, devastating vegetation and altering freshwater ecosystems. Rapid increases in atmospheric CO2 caused spikes in temperature, potentially raising tropical land temperatures by 10 to 15 degrees Celsius in geologically brief intervals. Flooded river basins alternated with drought-stricken lowlands, creating unstable habitats. Many large reptiles, including sauropodomorph precursors and their predators, were physiologically specialized for certain thermal and hydrological conditions and could not cope with such fluctuations. Meanwhile, smaller, more flexible organisms, dinosaurs included, could tolerate wider environmental ranges. They were not immune to extinction pressures, but their survival strategies allowed them to weather the storm better than many of their contemporaries. It is essential to understand that survival did not equate to invulnerability. Many early dinosaurs perished in these events, leaving only the hardiest lineages to persist. Fossil evidence indicates population bottlenecks. Diversity dropped sharply, and certain groups may have been reduced to a few isolated populations, but these survivors carried within them the seeds of future domination, traits that would allow explosive diversification in the Jurassic. Evolution is rarely a straight path. In this case, extinction created the conditions that would allow small, adaptable dinosaurs to occupy niches previously monopolized by much larger, more imposing reptiles. As the dust settled across Pangaea, the world was dramatically reshaped. Forests regrew on volcanic soils, rivers carved new courses across floodplains, and the climate began its long, chaotic recovery. The continents were still connected, allowing populations to disperse, but the ecosystem structure was unrecognizable. Dinosaurs moved quietly into this vacuum, their survival a testament to the power of persistence over brute force. Their upright stance, long strides, and relatively high metabolic rates provided a competitive edge in this unsettled world. They were not kings yet, but they were present, adaptable, and ready to exploit opportunities. It is here that the narrative of dinosaur dominance begins in earnest. The end Triassic extinction was not an event of heroic conquest. It was a reset, a planetary-scale dice roll in which the right combination of traits, strategies, and sheer luck determined survival. Dinosaurs did not claim the world by defeating their competitors in battle. They inherited the spoils left by catastrophe. As Steve Brusata has reflected, extinction is the ultimate enabler. It is indiscriminate, ruthless, and utterly transformative. Dinosaurs didn't rise to power because they were the strongest. They rose because they endured when the world did not. In this crucible, the dinosaurs' evolutionary potential was unleashed. Their body plans, initially subtle and unassuming, now offered extraordinary flexibility. Small bipedal theropods could hunt opportunistically, early sauropodomorphs could exploit sparse vegetation, and omnivorous forms could survive in marginal habitats. The ecological vacuum allowed not only survival, but experimentation, laying the foundation for the incredible diversity that would follow. The late Triassic collapse thus becomes both a story of extinction and a story of opportunity. One lineage survives, grows, and eventually dominates, while countless others vanish forever. By the dawn of the early Jurassic, roughly 201 million years ago, the stage was set for an evolutionary explosion. The world, scarred and reshaped by the end Triassic extinction, offered an almost unprecedented opportunity. Vast open ecological niches, few predators, and a climate still warm and humid enough to support rapid plant growth. Dinosaurs, once peripheral actors on the Triassic stage, now stepped into the spotlight. Their small, resilient lineages, honed by survival in a world gone mad, were ready to exploit every opportunity. This was not a slow ascent, it was a surge, a rapid expansion that would carry dinosaurs across continents, ecosystems, and evolutionary possibilities, marking the first chapter of their long, unbroken reign. The first wave of dinosaurian proliferation was subtle, yet profound. Small theropods, descendants of the modest bipedal hunters that had survived the extinction, diversified in both form and behavior. Their upright posture, parasagittal gait, and relatively high metabolism allowed them to explore niches that had previously been dominated by larger reptiles. While their ancestors had survived by stealth and opportunism, now their descendants adapted to become specialized predators, able to pursue prey across floodplains, dense forests, and coastal lowlands. These theropods, still small by later standards, exemplified the principle that adaptability, not sheer size, was the key to dominance in a world still unstable from volcanic upheaval. Meanwhile, the seeds of gigantism were planted among the sauropodomorphs. Early members of this lineage, which would later give rise to the colossal sauropods of the Jurassic and Cretaceous, began experimenting with herbivory on a scale never before seen. Their long necks, initially modest, allowed access to new strata of foliage. Their growing bulk, facilitated by efficient respiratory systems and a metabolism tuned to steady growth, conferred both digestive advantages and protection from the predators that had survived the extinction. Researchers such as Armand de Ricles and R.E.H. Reed, through meticulous study of bone histology, have demonstrated that these early sauropodomorphs were capable of rapid growth, reaching significant size in just a few decades, a stark contrast to many modern reptiles, which grow slowly and remain vulnerable for years. The early Jurassic was, in essence, a laboratory for evolutionary experimentation on a grand scale. This expansion was facilitated and shaped by the movements of the continents. The supercontinent Pangaea, though still largely intact, had begun its slow fragmentation. Rifts and drifting plates created new coastlines, shallow seas, and isolated land masses. These geographic shifts produced the first hints of faunal provinciality, where populations began to evolve separately due to geographic isolation. Northern regions saw the development of distinct theropod and prosauropod assemblages, while southern ecosystems nurtured forms that would eventually give rise to the gigantic sauropods of South America and Africa. Plate tectonics was not merely a geological phenomenon, it was a catalyst for biological diversity, creating isolated evolutionary laboratories where dinosaurs could diverge, specialize, and experiment with novel forms of locomotion, feeding, and social behavior. Among the herbivores, diversity began to radiate quickly. Prosauropods, long-necked but still relatively small and often facultatively bipedal, colonized forests and floodplains, browsing on ferns, cycads, and early conifers. The herbivorous niches they occupied were critical, shaping vegetation and influencing predator-prey dynamics. As they grew and diversified, their skeletal adaptations became more refined. Pneumatized vertebrae, seen in later sauropods, began appearing as a primitive mechanism to reduce skeletal weight, allowing longer necks and larger bodies. Teeth adapted to processing fibrous plants proliferated, signaling a shift toward ecological dominance. Meanwhile, smaller herbivorous forms explored niche partitioning, feeding on low vegetation, or occupying upland habitats where larger sauropodomorphs could not reach. Theropods continued to explore behavioral complexity during this period. The emergence of early coelurosaurs and ceratosaurs hinted at the cognitive and sensory sophistication that would characterize later predatory dinosaurs. Fossil evidence, including articulated skeletons and bone microstructure, suggests that these early Jurassic predators were not solitary hunters by default. Rather, they may have engaged in social behavior, cooperative hunting, or at least opportunistic pack feeding, a behavioral template that would become more elaborate in the Cretaceous. Their speed, agility, and high metabolic rates gave them an evolutionary edge over slower, more massive competitors that had survived the end Triassic extinction but were now dwindling under the pressure of specialized dinosaurs. By this point, the early Jurassic world was a patchwork of thriving ecosystems. Forested floodplains stretched across Pangaea, dotted with rivers and lakes where amphibians and turtles persisted. In the air, pterosaurs continued to diversify, occupying niches above the terrestrial fray. In the oceans, marine reptiles flourished, their aquatic dominion largely unaffected by the terrestrial reshuffling. Yet on land, dinosaurs were asserting their presence, moving from marginal participants to central figures in nearly every ecosystem. The combination of anatomical innovation, behavioral flexibility, and environmental opportunity set the stage for a planet-wide colonization, a process that would continue unabated for millions of years. It was during this phase that a fundamental divergence in dinosaur anatomy occurred, one that would echo through the remainder of the Mesozoic. Paleontologist Harry Govea Seeley, in the late 19th century, recognized a critical division in the pelvis, a structural adaptation that reflected deeper evolutionary trajectories. Dinosaurs split into two distinct lineages: Saurischia, the lizard-hipped dinosaurs, and Ornithischia, the bird-hipped dinosaurs. This was not a trivial taxonomic distinction. The pelvic orientation dictated muscle attachment, locomotion, and eventually the diversity of form and function each group could achieve. Saurischians, including the sauropodomorphs and early theropods, retained a forward-pointing pubis, supporting bipedal locomotion and eventually massive quadrupedal giants. Ornithischians, evolving backward-pointing pubic bones, would pave the way for sophisticated herbivores with advanced chewing mechanisms and complex social structures. This divergence was a kind of evolutionary bifurcation, an anatomical fork in the road that would define Mesozoic life. The early Jurassic was a crucible of both opportunity and innovation. Dinosaurs did not simply fill empty niches. They experimented with form, function, and behavior in ways no lineage had before. The continents were shifting, climates were unstable but fertile, and the ecological vacuum left by extinct Triassic reptiles created a world rich with unclaimed resources. Sauropodomorphs were stretching toward gigantism, theropods were refining predatory strategies, and ornithischians were preparing quietly for their later flourish. Diversity, experimentation, and adaptability were now encoded into the DNA of a lineage that had once been small and peripheral. From the first tentative steps after the end Triassic extinction to this sweeping expansion, dinosaurs were no longer the marginal survivors of chaos. They were the architects of the next chapter of terrestrial life. Their spread across Pangaea, their anatomical divergence, and their rapid ecological experimentation set the stage for the dramatic, world-spanning dominance that would define the Jurassic and beyond. Yet even as they began to claim every continent and every habitat, evolution had more in store. The success of dinosaurs would not be measured merely by their presence or abundance. It would be measured by the forms they would take, the giants they would become, and the ecological revolutions they would provoke. And it was precisely at this moment of expansion, at the very cusp of their rise, that dinosaurs faced the most critical structural decision of their evolutionary journey. To dominate the planet fully, to exploit every niche and every opportunity, they would need form as well as function. The split that began in the pelvis, subtle and anatomical, would determine the fate of all future dinosaurs, dividing them into two grand lineages that would experiment separately with locomotion, feeding strategies, and body plans. Every step of the early Jurassic expansion, every herd, every predator-prey encounter, every stretch of long neck toward high foliage, was a rehearsal for the diversity and spectacle that would soon follow. The world had opened its doors to the dinosaurs. They had survived by endurance, thrived by flexibility, and now, with the stage set, the architecture of their bodies and the blueprint of their evolution would take them down two radically different paths, defining the rest of the Mesozoic. Subscribe now and continue this journey into the rise, diversity, and eventual fate of the creatures that ruled Earth for nearly 180 million years. By the Middle Jurassic, dinosaurs had begun to saturate every habitable niche on land, yet beneath this outward spread, a quieter but no less profound transformation was taking place. Evolution, ever experimental, had begun to etch deep anatomical divisions into the bodies of these creatures. It was a split that would dictate the trajectory of nearly every dinosaur for the rest of the Mesozoic. This was the moment of the Great Divide, the bifurcation into two major lineages, Saurischia and Ornithischia, a division that was subtle in form but monumental in consequence. The groundwork for this understanding had been laid in the late 19th century by Harry Govier Seeley. By examining the pelvic structures of a wide array of dinosaur fossils, Seeley noticed a striking pattern. Some species retained a forward-pointing pubis, while others evolved a backward-oriented arrangement. These differences were not trivial. The orientation of the pelvis determined the attachment of muscles used in locomotion and digestion, which in turn shaped posture, gait, and ultimately the ecological strategies available to each lineage. In Saurischians, the lizard-hipped dinosaurs, the forward-pointing pubis supported bipedal movement in smaller theropods and later massive quadrupedal frames in sauropods. Muscle architecture favored strong, propulsive hind limbs, essential for both pursuit and the support of immense body mass. In Ornithischians, the bird-hipped dinosaurs, the backward-facing pubis allowed for an expanded gut cavity, supporting more efficient digestion of fibrous plant material and freeing forelimbs for defensive structures, social interaction, or manipulation of vegetation. This divergence was more than anatomy, it was a philosophical split in evolutionary strategy. Saurischians were built for motion, for pursuit, for predation, and the eventual construction of gigantism. Ornithischians were built for endurance, for processing, and for survival through ecological cleverness rather than sheer size. The two groups represent a dichotomy that echoes throughout natural history. One lineage prioritizing power and size, the other complexity and versatility. Each strategy carried its own rewards and risks. Neither was inherently superior. Each was an answer to the same question posed by the environment: how to persist in a world of shifting landscapes, changing climates, and evolving competitors. Among the Saurischians, early theropods continued to refine their bipedal efficiency. Fossil evidence suggests that small to medium-sized predators were developing more advanced sensory capabilities, keen vision, acute olfaction, and rapid reflexes that allowed them to track agile prey. Muscle attachments on the pelvis and femur indicate a stride efficiency that could rival modern cursorial predators, a trait essential for their survival in a landscape dotted with opportunistic competitors. These early theropods, though not yet apex predators in the scale of later Tyrannosaurus or Allosaurus, were laying the foundation for a lineage that would dominate terrestrial carnivory for tens of millions of years. At the same time, early sauropodomorphs were exploiting a different pathway. Their pelvis and hind limb anatomy supported increasing body mass while still maintaining mobility. Pneumatized vertebrae, lightened bones with air sacs, allowed them to expand their necks and reach vegetation previously inaccessible. The shape of their hips and muscle attachments indicate a combination of quadrupedal and facultative bipedal locomotion, a flexibility that would become essential as they evolved into the colossal sauropods of the late Jurassic. The Saurischian path, in essence, was one of spatial dominance, the ability to move, reach, and control territory through sheer physical presence. Meanwhile, ornithischians, those smaller and less conspicuous during this period, were exploring entirely different evolutionary experiments. Their pelvic structure facilitated enormous gut capacity, supporting a diet of tough, fibrous plants. The structure of the jaw in some lineages shows evidence of early adaptations toward complex chewing, a process that would only intensify in the Cretaceous with the advent of dental batteries and advanced masticatory mechanisms. Ornithischians were also experimenting with social behavior and defense. Armor plates, spikes, and eventually horns would emerge as solutions to predation, not through attack, but through deterrence and survival. They were not built for speed or raw power. They were built for persistence and resource extraction, for exploiting what others could not. This divergence also had profound ecological consequences. As the Saurischians expanded into predator and mega-herbivore roles, Ornithischians carved out complementary herbivorous niches, occupying environments where mobility and digestion strategy provided a competitive advantage. Ecosystems became increasingly structured, predator-prey dynamics grew more complex, herbivore guilds diversified, and spatial distribution of species began to reflect both anatomical and behavioral specializations. In a sense, the two lineages were co-constructing the Mesozoic world, one shaping the landscape through movement and foraging patterns, the other by refining dietary efficiency and defense. Geography further amplified these differences. Continental drift was gradually fragmenting Pangaea, creating barriers and corridors that promoted regional differentiation. In the north, Saurischians began experimenting with early gigantism, stretching necks and limbs, and occupying plains and floodplains. In southern regions, Ornithischians explored dense forests and complex terrains, where their digestive innovations and defensive adaptations allowed them to persist despite the presence of larger predators. Natural selection favored these different strategies in parallel, reinforcing the anatomical split identified by Seeley. Fossil evidence from the Middle to Late Jurassic also demonstrates that the divide was not merely anatomical, but deeply functional. Saurischians' hip and limb arrangements favored explosive bursts of speed, or the support of enormous mass depending on lineage, while Ornithischians' pelvic orientation allowed for prolonged foraging and a more energy-efficient metabolism. This functional divergence meant that the two lineages rarely competed directly for the same ecological niches, a separation that enhanced their survival and allowed them to radiate widely across the planet. By the end of this period, the Mesozoic world had effectively split into two empires. On one side were the Saurischians, building toward gigantism, experimenting with carnivory, and setting the stage for the dramatic apex predators of the Jurassic and Cretaceous. On the other side were the Ornithischians, quiet innovators, perfecting herbivory, defense, and social structures that would later culminate in elaborate ceratopsians, stegosaurs, and ankylosaurs. The distinction was invisible to a casual observer of the fossil record at first, but it was encoded in the very skeletons of the animals, a blueprint that would dictate evolutionary possibilities for millions of years. The philosophical weight of this divide is subtle but profound. Evolution does not always reward size, speed, or immediate dominance. Sometimes it rewards experimentation, partitioning, and the clever exploitation of ecological opportunity. Saurischians and Ornithischians embody two complementary strategies, one reaching outward and upward, the other refining inward and backward, each essential to the rich tapestry of Mesozoic life. This duality created a world in which success was not monolithic but multifaceted, a world in which survival could be expressed as motion, power, persistence, or ingenuity. In the unfolding story of dinosaurs, this anatomical schism marked a moment of profound creativity. The paths of these two lineages would diverge further, yet they were already shaping the ecosystems around them. Predators learned to chase, herbivores learned to defend, and the balance of life shifted subtly but inexorably. From these two strategies would arise the giants that dominate our imagination and the armored, cunning herbivores that remind us that survival often depends on restraint as much as aggression. One path led to the creation of colossal landscapes of flesh and bone, the other to weapons of precise evolution, jaws honed to efficiency and defense refined to art. In the silent, sprawling forests and floodplains of the Jurassic, the two empires were quietly taking form, each poised to experiment with the limits of size, shape, and survival, carrying the story of life forward in two entirely different directions. The story of life's scale finds no more dramatic expression than in the emergence of the sauropods, the colossal herbivores that would define the Jurassic and Cretaceous landscapes. These were animals of unprecedented size, the largest terrestrial creatures ever to walk the Earth, yet their existence was far from inevitable. The first sauropodomorphs had been relatively modest, lightly built, bipedal or facultatively quadrupedal, and confined to small niches where predation and resource availability permitted. But by the Middle Jurassic, evolution had begun to push this lineage toward extremes, exploiting the ecological opportunities created by the extinction of earlier dominant reptiles and the continued diversification of vegetation. Sauropods like Diplodocus and Brachiosaurus represent a triumph of anatomical innovation. Their skeletons reveal a mastery of weight management that challenges our imagination. The vertebrae, ribs, and even skull bones were extensively pneumatic, hollowed and reinforced with struts, a structural solution that allowed enormous size without collapsing under one's own weight. Martin Sander, a leading paleobiologist studying sauropod morphology, notes, "These animals were living experiments in scaling. Every vertebra, every limb is a compromise between strength, mobility, and metabolic efficiency." Pneumaticity not only lightened their skeletons but also likely interfaced with an air sac-based respiratory system, similar in principle to modern birds, facilitating efficient oxygen delivery to sustain their massive bodies. Growth rates in sauropods were equally remarkable. Armand de Ricles's histological studies of fossilized bone tissue show that sauropods could add hundreds of kilograms in months, reaching adult size in less than 2 decades in some species. Unlike the slow-growing reptiles of today, these giants combined the metabolic efficiency of archosaurian physiology with continuous growth strategies, allowing them to exploit the abundance of plant matter across Mesozoic floodplains, forests, and open woodlands. R.E.H. Reed's research into their skeletal microstructure confirms that sauropods did not grow intermittently or slowly in response to environmental stress. They grew consistently and rapidly, a testament to evolutionary fine-tuning in both physiology and ecology. It is critical to correct a lingering misconception. These giants were not swamp-bound or semi-aquatic as once imagined. Early interpretations likened Brachiosaurus or Diplodocus to living barges floating in shallow water to support their weight. However, detailed studies of limb bone strength, joint articulation, and muscle attachment indicate that these animals were fully terrestrial, walking the floodplains and forests with remarkable stability. Martin Sander emphasizes, their limbs are not columns of floating tissue. They are engineered for terrestrial locomotion. Every step required careful coordination, but it is clear they were entirely land-adapted. This adaptation allowed them to access a variety of vegetation strata, from low-lying ferns to towering conifers, expanding the vertical reach of herbivory to levels unmatched by any other terrestrial animal. The global distribution of sauropods also speaks to the rapidity and extent of their expansion. As Pangaea fragmented and land masses drifted apart, sauropods dispersed across Laurasia and Gondwana, evolving regional specializations along the way. Argentinosaurus, for instance, reached lengths exceeding 35 meters in South America, while Brachiosaurus dominated North American floodplains with a different body plan optimized for high browsing. Each lineage reflects subtle differences in limb proportions, vertebral structure, and even neck length, all dictated by environmental pressures and resource competition. These animals were the engines of herbivory, consuming vast quantities of plant matter, processing it with large guts, supported by their distinctive pelvic and ribcage architecture, and redistributing nutrients through their massive movements across the landscape. Sauropods were not merely passive consumers of vegetation, they actively reshaped their ecosystems. Their foraging patterns created gaps in forests, altered plant community compositions, and facilitated seed dispersal, acting as ecological engineers. Histological evidence combined with trackways suggests that some sauropods may have traveled in small groups or loosely associated herds, though not tightly coordinated like later mammalian megaherbivores. Even in solitude, their sheer size meant that every step left a footprint in the ecosystem, literally and figuratively, influencing vegetation and soil structure. Despite their scale and seeming invulnerability, these giants were not exempt from evolutionary pressures. Predation played a constant role in shaping their early lives. Juvenile sauropods, though smaller, were vulnerable to theropod predators, requiring rapid growth to reach a size where few could threaten them. Fossil evidence from trackways and bone beds shows that these predators were opportunistic and adapted to hunting in the same environments as the sauropods, honing speed, agility, and pack coordination. Sauropod defenses were subtle. Sheer mass, long tails capable of delivering powerful strikes, and herd dynamics rather than direct aggression or armor provided protection. Evolution was continuously negotiating a balance between scale and vulnerability, an arms race written in bone. The sauropod's rise also illuminates a broader evolutionary principle: the relationship between resource abundance and body size. The Middle and Late Jurassic saw expansive forests and wetland systems capable of sustaining enormous herbivores. Unlike carnivores, whose numbers are limited by prey availability, herbivores can expand in proportion to the biomass they consume. In this context, the evolution of extreme gigantism was not an anomaly, but a predictable outcome of abundant food and selective pressures favoring survival through size. R.E.H. Reed remarks, "When conditions permit, evolution does not hesitate to explore extremes." The sauropods are the perfect example of this principle. Where there is ecological space and energy, life scales upward. Interestingly, this period also set the stage for later evolutionary innovations. The physiological and skeletal features that allowed sauropods to achieve enormous size would become templates for diversification. Neck elongation, vertebral pneumaticity, and limb robustness were not static traits. They were subject to refinement over tens of millions of years, producing a staggering array of forms. Alamosaurus, appearing much later in the late Cretaceous, represents the culmination of these trends in North America, a distant echo of the Middle Jurassic pioneers that first pushed the limits of herbivorous gigantism. The lineage's persistence underscores the long-term success of the design choices made in this early period: mobility combined with scale, structural innovation, and efficient metabolism. Philosophically, the story of the sauropods is a meditation on the possibilities of life under optimal conditions. These were animals capable of towering over forests, moving with deliberate yet powerful grace, and fundamentally reshaping their world without conscious intent. They were a demonstration that evolution is not linear nor goal-directed, but opportunistic, experimental, and capable of achieving forms that exceed human imagination. They were the ultimate experiment in herbivory and terrestrial gigantism, a testament to what life can become when ecological opportunity meets evolutionary innovation. Yet, even as these giants roamed, the stage was not empty. Predators were evolving, adapting to exploit every weakness. Theropods were becoming more specialized, faster, and more coordinated. Sensory systems sharpened, claws and teeth became more efficient, and intelligence relative to body size began to matter in hunting strategies. The rise of predators imposed selective pressures that would continue to shape sauropod life histories, from growth rates to social behavior, ensuring that no evolutionary advantage remained uncontested. The sauropods illustrate that maximum scale does not equate to dominance in a static sense. It is one dimension in the complex matrix of survival, reproduction, and ecological interaction. They demonstrate that even the largest, most seemingly invincible forms are part of a broader narrative, subject to pressures from predators, environmental change, and the relentless march of evolution. Their story bridges the gap between anatomy and ecology, physiology and planetary impact, revealing the extraordinary interdependence of life's structures and strategies. In the vast forests and floodplains of the Jurassic, these giants moved as engines of energy, shaping the land, cycling nutrients, and asserting a presence that would define the landscapes for millions of years. Yet they were part of a dynamic system, never alone, always tested by predators and competition, and constantly negotiating the precarious balance between opportunity and vulnerability. The emergence of sauropods was not merely a chapter in dinosaur evolution. It was a profound lesson in the possibilities of life, a monument to scale, and a prelude to the ongoing interplay between predator and prey, between innovation and survival, that would continue to shape the Mesozoic world. The story of gigantism in the dinosaur lineage reveals the delicate balance of form, function, and ecological context. The enormous herbivores were successful not only because of their size, but because of how size was integrated into a broader set of anatomical, physiological, and ecological strategies. They were fully terrestrial, dynamically interacting with their environments, and setting the stage for evolutionary arms races that would define the Mesozoic. Life, as always, was experimental, adaptive, and ceaselessly inventive. But even as the Earth trembled beneath the steps of these giants, the other side of the evolutionary equation, predation, was advancing in lockstep. Carnivores were refining their hunting strategies, intelligence, and morphology, preparing for the challenges of confronting the largest creatures to have ever walked the planet. Evolution, as it had throughout Earth's deep history, remained a dialogue, not a monologue, a balance between the capacity to dominate and the capacity to survive. Long before the dinosaurs became icons of raw power and massive scale, their evolutionary cousins on the other side of the Saurischian divide were quietly developing a different kind of dominance, one measured not by mass or height but by agility, intellect, and adaptability. The theropods, the bipedal predators, began as small, nimble hunters, but over tens of millions of years, they evolved a sophistication that would ultimately set the stage for the rise of birds, the only lineage of dinosaurs to survive the K to PG extinction. Understanding this path requires looking closely at anatomy, behavior, and evidence from the fossil record that challenges our traditional view of dinosaurs as purely instinct-driven monsters. One of the most pivotal discoveries in modern paleontology came from John Ostrom in the 1960s, whose detailed study of Deinonychus antiropus transformed the way scientists thought about theropod behavior. Ostrom noticed an unusual combination of features: a large, sickle-shaped claw on the second toe, a lightly built but powerful skeleton, and an articulated bird-like pelvis. Deinonychus was not the lumbering brute we imagined, Ostrom explained. It was a creature of precision, of coordinated movement, built for speed and dexterity. It hunted actively, perhaps in packs, and it thought. The concept of pack hunting in theropods remains debated, but fossil sites preserving multiple individuals together, along with healed bite marks on bones of conspecifics, suggest at least some social or cooperative behavior, a radical departure from the image of solitary, instinct-driven predators. This social and cognitive sophistication is mirrored in skeletal and cranial anatomy. Theropod skulls were highly kinetic, with multiple joints allowing a wide gape and precise control of jaw motion. This enabled them to seize, manipulate, and tear prey with greater efficiency. Eye sockets were positioned to allow binocular vision, enhancing depth perception critical for calculating strikes on agile prey. Neurological studies inferred from endocasts of fossil skulls indicate relatively large brain-to-body ratios, particularly in the cerebellum and forebrain, hinting at coordination, balance, and possibly complex behavior. Thomas Huxley in the 19th century had famously called birds living dinosaurs, a statement that now finds its deepest meaning in theropods. The seeds of flight, feathered insulation, and behavioral complexity were present long before the first wings took shape. Feathers, once thought to be unique to birds, are now recognized across a range of theropod species. Fossils of Velociraptor from the late Cretaceous, for example, preserve quill knobs on the forearm, attachment points for feathers. This anatomical detail, corroborated by Xu Xing's work in China on feathered dromaeosaurids and troodontids, indicates that feathers evolved before powered flight and likely served multiple purposes: thermoregulation, display, camouflage, and even tactile function. The emergence of feathers represents an evolutionary innovation that reshaped theropod ecology, enabling more sophisticated predator-prey interactions and creating the anatomical foundation for later aerial experimentation in the lineage that would give rise to birds. Behaviorally, theropods show evidence of complex hunting strategies. The anatomy of Deinonychus, including stiffened tails that acted as dynamic counterbalances, allowed sudden turns and rapid strikes. Fossil trackways suggest coordinated movement in some species, implying at least occasional group hunting or socially aware foraging. In larger theropods, such as Tyrannosaurus rex, bone histology reveals growth patterns and metabolic strategies indicative of a highly active predator, capable of bursts of speed and sustained pursuit. Studies by paleontologists like Gregory Erickson indicate that juvenile tyrannosaurs were likely faster and more agile than adults, creating a dynamic where hunting strategies evolved over the life cycle, balancing risk, opportunity, and energy efficiency. Intelligence in theropods extended beyond hunting. Sensory adaptations show acute hearing, smell, and vision, while forelimb morphology in some species suggests the capacity for manipulation. This combination of motor control, sensory input, and social awareness created a behavioral flexibility that would have allowed theropods to respond to changing environments, avoid competition, and exploit new ecological niches. The very fact that some of these lineages survived the end Cretaceous extinction event in the form of birds attests to the success of these strategies. Survival was a question of adaptation, not just predation. Theropods were not uniform in their approach. Small, fast dromaeosaurids exemplified agility and precision. Medium-sized troodontids may have combined hunting with opportunistic omnivory, and giant tyrannosaurids relied on brute strength, augmented by sensory acuteness and metabolic efficiency. Each group reveals the diversity of evolutionary experiments occurring within a single clade. This internal diversification parallels the Saurischia split in herbivores, where sauropods explored gigantism, theropods explored complexity, intelligence, and integration with the environment. The fossil record also reveals the importance of developmental plasticity in theropods. Growth series of Tyrannosaurus and other large carnivores show that juveniles and adults occupied different ecological niches, reducing intraspecific competition. Smaller, faster juveniles hunted different prey than the adults, while larger adults could target mega-herbivores, showing a remarkable strategy of resource partitioning over a lifetime. This ontogenetic niche differentiation represents an advanced form of ecological planning encoded by natural selection, highlighting that dominance is not always about raw size or strength, but about timing, coordination, and adaptability. Furthermore, the appearance of feathers and other avian-like characteristics in theropods illustrates an evolutionary trajectory that intertwines anatomy, physiology, and behavior. Feathers were initially for insulation, then display, then gliding, and finally flight. Brain structure evolved alongside sensory and motor abilities, suggesting a feedback loop where cognition and physical capability enhanced each other. The eventual emergence of birds is not a sudden revolution, but the culmination of tens of millions of years of incremental experimentation, where intelligence, agility, and social behavior created new survival strategies under shifting environmental pressures. Theropod evolution also challenges conventional notions of competition. Predation was only one axis of survival. Successful species were those that could navigate ecological networks, learn, adapt, and cooperate when necessary. John Ostrom's observations on Deinonychus emphasized that these were not mindless killers. They were hunters that thought, strategized, and coordinated. Xu Xing's discoveries reinforce that even small theropods possessed anatomical traits for nuanced interaction with their environment, suggesting that intelligence and dexterity were selected alongside raw predatory capability. These innovations, combined with feathers, social hunting, and sensory acuity, laid the groundwork for survival in fluctuating ecosystems long before the first true birds appeared. The trajectory of theropods highlights a subtle philosophical truth about evolution. Power alone does not guarantee longevity. While giants like sauropods reached forms of maximal herbivorous scale, theropods explored the dimensions of behavior, cognition, and anatomical sophistication. Their success depended on adaptability, on exploiting niches, on cooperation, and on the capacity to respond to threats with speed and strategy rather than brute force. Life is not merely a contest of strength, it is a dialogue between organism and environment, predator and prey, instinct and innovation. By the late Cretaceous, theropods had diversified into a range of forms, from the swift, feathered hunters stalking small mammals and lizards, to colossal apex predators dominating the landscapes, to specialized lineages capable of flight. This spectrum of forms demonstrates the evolutionary versatility of the group and sets the stage for the modern avian lineage. Birds today are living testimony to the enduring legacy of these hunters and thinkers, a lineage that embraced the complexity of life rather than the simplicity of dominance. Even as theropods ruled land in forms both large and small, their evolutionary narrative illuminates the delicate balance of Mesozoic ecosystems. Predation was intertwined with social interaction, cognition, and environmental adaptation. Feathers, sharp claws, stereoscopic vision, and high metabolic rates were all components of a survival strategy that was far more than mere hunting. They were experiments in life, tests of intelligence, and innovations in behavior that would echo across millions of years. Survival, in the end, was not about the ability to kill. It was about understanding, adapting, and living in concert with the challenges of an ever-changing world. The theropods teach that evolution rewards nuance, that the sharpest predators are often the most thoughtful, and that the seeds of survival may lie not in conquest, but in cooperation, strategy, and foresight. Long before humans began recording the rhythms of life, dinosaurs had already evolved complex societies that rivaled many of the social behaviors we see in modern animals. For decades, paleontologists pieced together evidence from footprints, bone beds, and fossilized nests, revealing a picture of creatures that were far from solitary monsters. They were social, cooperative, and in many ways deeply attentive to their young and to one another. Their story is one of life organized at a scale and sophistication that allowed these animals to thrive in a world that was constantly shifting beneath their feet. One of the earliest indications of social behavior in dinosaurs came from trackways, such as those studied extensively by Roland T. Byrd in the early 20th century. Byrd's meticulous mapping of parallel dinosaur footprints revealed lines of movement where multiple individuals walked together, sometimes across vast distances. These patterns were more than random wanderings. They suggested herding behavior, coordinated movement, and possibly seasonal migrations. In some locations, trackways include individuals of varying sizes, indicating mixed-age groups. This reveals not just the presence of family units, but complex social structures where younger and older dinosaurs move together, a strategy that could enhance survival through protection, guidance, and shared vigilance. Fossilized bone beds further reinforce the notion that many dinosaur species were social animals. Sites like the famous Camarasaurus and Maiasaura bone beds show hundreds of individuals preserved together. In some cases, these assemblages suggest catastrophic deaths during floods or other environmental upheavals, but the repeated discovery of multiple individuals of the same species in proximity points to habitual grouping rather than coincidence. Scientists like John R. Horner have argued that these bone beds reflect long-term social behavior, implying that herding was a fundamental survival strategy. Living in groups would have allowed herbivorous dinosaurs to reduce predation risk, coordinate feeding, and even share knowledge about resources and threats, a kind of collective intelligence encoded in behavior over generations. Perhaps the most compelling evidence for social complexity comes from nesting sites. Egg Mountain in Montana, excavated by Horner and his team in the 1970s, revealed densely packed nests of Maiasaura, the good mother lizard. Unlike many modern reptiles which lay eggs and abandon them, these dinosaurs exhibited remarkable parental care. Fossilized remains of hatchlings indicate that juveniles remained near the nests for extended periods, cared for by adults. This suggests feeding, protection, and teaching behaviors that required sophisticated social interaction. In some nests, the layering of eggs and evidence of repeated use indicates site fidelity, where generations return to the same locations to reproduce, a behavior reminiscent of modern seabird colonies and mammals. Such evidence challenges the stereotype of dinosaurs as purely instinct-driven killers or mindless giants. Herding and nesting required coordination, communication, and recognition of individuals. Vocalizations may have played a role, although soft tissue rarely preserves. Modern analogues from birds to crocodilians suggest a rich repertoire of sounds for signaling danger, coordinating movement, or calling young. Additionally, some species exhibited sexual dimorphism or ornamentation, suggesting that social interactions extended to mating displays and intra-group hierarchies, further emphasizing their behavioral sophistication. Migration is another layer of social complexity in dinosaur societies. Fossil evidence indicates that some species, particularly large herbivores like sauropods, engaged in seasonal migrations to exploit food resources across vast territories. Footprint trails extending for kilometers, combined with isotopic analysis of teeth, demonstrate that these dinosaurs moved in regular patterns, likely following ancient river valleys, floodplains, or coastal plains. Migration in herds would have required memory, spatial awareness, and communication among members, a dynamic social system that mirrors the most advanced behaviors of modern elephants and caribou. It also highlights the adaptability of dinosaurs. Their social structures were not static, but responsive to environmental pressures, balancing competition, predation, and resource availability. The interplay of herding, nesting, and migration illustrates the multidimensional social lives of dinosaurs. Herding allowed collective defense against predators, migration enabled resource optimization, and nesting ensured the survival of the next generation. These behaviors, while seemingly simple in isolation, together reveal a network of social strategies that were crucial for long-term survival. In species like Maiasaura, parental investment likely improved juvenile survival rates significantly, suggesting that selection favored individuals capable of cooperation and social coordination. Such dynamics also offer insight into the evolutionary trajectory of birds, where many behaviors, flocking, nesting, and parental care, have deep roots in these Mesozoic ancestors. Fossil evidence even hints at intra-group roles. In some trackways, larger individuals appear to flank smaller ones, a potential defensive arrangement to shield the young. In others, juvenile footprints indicate exploratory behavior, possibly learning the boundaries and hierarchy of the herd under the watchful eyes of adults. The sophistication of these interactions implies not just instinct, but learning, memory, and perhaps rudimentary culture. Knowledge passed across generations through repeated behaviors. Dinosaurs were shaping their societies in real time, responding to environmental challenges with cooperative strategies that ensured their survival across millions of years. Social living also influenced evolutionary pressures. Herding and nesting may have selected for intelligence, sensory acuity, and communication abilities. Predators, in turn, evolved in response to these strategies, leading to an arms race where behavioral sophistication became as crucial as physical power. Pack hunters such as dromaeosaurids and tyrannosaurids were likely adapting to the social defenses of herbivores, refining tactics and hunting strategies that required coordination and planning. In essence, dinosaur societies created the conditions for co-evolution, a dynamic interplay that shaped Mesozoic ecosystems at every level. Yet these sophisticated social systems existed against a backdrop of a constantly changing world. Climatic shifts, volcanic events, and fluctuating sea levels meant that herds had to adapt quickly, nests had to be relocated, and migrations had to respond to environmental uncertainty. The evidence from trackways and bone beds suggests that dinosaurs were remarkably resilient, capable of adjusting their social strategies to survive in volatile conditions. Their societies were flexible, evolving not just physical traits but behaviors that allowed them to exploit ecological opportunities while mitigating risks. Ultimately, the story of dinosaur societies reveals a world of complexity and interconnection. Herds, migrations, and nesting behaviors demonstrate that survival was a collective endeavor as much as an individual one. Life was not merely a contest of strength or speed, but a balance of cooperation, learning, and responsiveness to the environment. Dinosaurs were not just inhabitants of the Mesozoic, they were participants in an intricate network of relationships, each species contributing to the rhythm of life on Earth. Their social structures laid the foundation for later evolutionary innovations, echoing through birds and mammals alike, and reminding us that intelligence and care can be as powerful a force in nature as claws and teeth. And still, the world was changing beneath their feet. By the late Cretaceous, around 66 million years ago, dinosaurs had reached a level of diversity and ecological dominance unmatched in the history of terrestrial life. Fossil evidence from sites like Nashoy Bito in northwestern New Mexico reveals an astonishingly complex ecosystem, one that existed barely 340,000 years before the Chicxulub impact would end the reign of these extraordinary creatures. Contrary to the long-standing narrative of a declining dinosaur world, this site demonstrates that dinosaurs were still thriving, occupying every ecological niche, from the colossal herbivores that shaped landscapes to the apex predators that hunted them. Nashoy Bito preserves a snapshot of a flourishing late Cretaceous ecosystem. The site has been meticulously studied using modern techniques such as magnetostratigraphy and radiometric isotope dating, providing a precise chronological framework. Magnetostratigraphy aligns the orientation of magnetic minerals in rocks with Earth's historical magnetic field reversals, allowing researchers to determine the relative ages of strata with remarkable accuracy. Radiometric isotope dating, particularly of isotopes like uranium and lead, confirms the absolute ages of these deposits. Together, these methods ensure that the fossils unearthed here represent the final chapters of non-avian dinosaur life in North America, far from a dying lineage. Among the dominant species at Nashoy Bito was Alamosaurus sanjuanensis, a titanic sauropod and one of the last of its lineage in North America. Alamosaurus could reach lengths exceeding 30 meters and weigh upwards of 70 tons, making it one of the largest animals ever to walk the continent. Like its Jurassic ancestors, Alamosaurus was a long-necked plant-eating giant, feeding on conifers, ferns, and flowering plants that flourished in the late Cretaceous. Its immense size was both a defense against predators and a testament to the efficient growth strategies seen in sauropods. Pneumatic bones reduced skeletal weight, and rapid juvenile growth ensured survival in a predator-rich environment. Predatory niches were filled by Tyrannosaurus rex, the apex predator of North America. Evidence from bone pathology, bite marks, and limb anatomy suggests that T. rex was an active hunter capable of ambush predation, social coordination, and sophisticated sensory processing. Its massive skull, filled with serrated teeth up to 30 centimeters long, could crush bone, allowing it to feed efficiently on both living prey and carrion. Paleontologist Steve Broussat notes, even in the shadow of the approaching asteroid, Tyrannosaurus was a creature at the peak of its power, a predator perfected by millions of years of evolution. The herbivorous landscape was enriched by species like Torosaurus, a ceratopsid with a striking frill and long brow horns. Ceratopsids like Torosaurus were likely social animals, moving in herds that offered protection against predators like Tyrannosaurus. Their frills and horns were multifunctional, used in defense, species recognition, and potentially in sexual selection. Alongside them, hadrosaurs, the duck-billed dinosaurs, roamed in vast herds, capable of complex vocalizations and perhaps even cooperative care of their young. Ankylosaurs, the armored quadrupeds with club-like tails, patrolled the understory, their bony armor and tail weapons providing formidable defense against carnivores. Nashoy Bito also highlights an important aspect of late Cretaceous ecosystems, regional diversity. These dinosaurs were not evenly distributed, rather, distinct faunal provinces existed across North America. The Nashoibito assemblage represents the southwestern province, where giant sauropods like Alamosaurus coexisted with large theropods and a variety of herbivorous dinosaurs. Comparative studies with sites in Montana or Alberta revealed different community compositions, suggesting that dinosaurs had already adapted to regional environments and resource distributions. They were not struggling to survive. They were specialists, each species finely tuned to its ecological niche. Perhaps most striking is that this snapshot directly challenges the myth of a declining dinosaur population. Some earlier hypotheses suggested that dinosaurs were in long-term decline before the K-PG extinction, perhaps due to climate changes or competition with emerging mammals. But the Nashoibito evidence tells a different story. Here, dinosaurs were abundant, diverse, and ecologically dominant right up until the end. Had they not been struck by the Chicxulub asteroid, there is every reason to believe that dinosaurs would have continued to thrive and evolve, just as mammals were poised to do in a different context. Dan Pepe emphasizes, this site shows us that dinosaurs were far from fading. They were vibrant, dynamic, and fully capable of surviving in their ecosystems until the sudden, catastrophic intervention from space. Behaviorally, this ecosystem likely mirrored the complex social structures seen elsewhere. Sauropods like Alamosaurus may have moved in herds, communicating over long distances through low-frequency sounds. Tyrannosaurus, while apex predators, may have hunted juveniles and weaker adults from herds, exerting selective pressure that reinforced herd dynamics. Herding and migration patterns would have been integral to survival in the shifting Cretaceous landscapes, ensuring access to water and forage during seasonal fluctuations. Nesting sites were probably scattered throughout floodplains, with parental care observed in many species, reflecting a continuity of social strategies that had evolved over millions of years. The plant life of Nashoibito also shaped these ecosystems. Conifers, cycads, ferns, and early flowering plants provided both food and habitat. Herbivores like hadrosaurs could exploit diverse vegetation with specialized teeth capable of grinding tough plant material, while sauropods fed at heights unreachable by other species. The intricate web of predator-prey interactions, combined with environmental diversity, reveals a fully functioning ecological network, balanced, resilient, and sophisticated. In sum, the late Cretaceous of Nashoibito presents dinosaurs at their zenith. They were thriving in diverse, regionally distinct ecosystems, exhibiting complex social behavior, remarkable physiological adaptations, and ecological mastery. Their dominance was not a matter of chance, but the result of tens of millions of years of evolutionary refinement. Yet even in this flourishing world, there was an unacknowledged threat, an incoming catastrophe that would abruptly reshape life on Earth. They were thriving, and the sky was about to fall. On a seemingly ordinary day, some 66 million years ago, a celestial interloper hurtled toward Earth at a speed that defies ordinary comprehension, over 20 kilometers per second. This was no comet or wandering fragment of ice. It was the Chicxulub asteroid, a dense body tens of kilometers wide, carrying within it the potential to end an era. When it struck the Yucatan Peninsula in present-day Mexico, the energy released was equivalent to billions of atomic bombs detonating simultaneously. The crater it carved measured over 180 kilometers in diameter and plunged nearly 20 kilometers into the Earth's crust, leaving a mark that would endure for millions of years, silent testimony to one of the most cataclysmic events in the planet's history. The immediate effects were apocalyptic. The impact generated colossal shockwaves that radiated across the planet, rupturing the crust and triggering earthquakes far stronger than any human could imagine. It launched billions of tons of debris into the atmosphere, creating a firestorm that incinerated forests and grasslands for hundreds of kilometers. Paleontologists and geophysicists reconstruct this inferno as a global phenomenon. Thermal radiation so intense that it ignited surface vegetation almost instantly, while ejecta rained down on a world already trembling from the force of impact. Fires blazed simultaneously on every continent, leaving behind a layer of soot that would eventually settle as evidence in the geologic record. Within hours, the atmosphere itself had been transformed. Dust, soot, and vaporized rock enveloped the planet, blocking sunlight and plunging Earth into a sudden darkness. Photosynthesis stalled, collapsing primary food chains almost immediately. Temperatures dropped sharply in a phenomenon now called an impact winter, reminiscent of a nuclear winter scenario where days became weeks and weeks became months of near-total gloom. This global blackout, combined with the disruption of climate and weather patterns, stressed ecosystems to the brink of collapse. In the oceans, massive tsunamis generated by the impact scoured coastlines and stirred nutrient-poor deep waters, disrupting marine food webs. But the story of extinction at the KPG boundary is not a tale of a single, solitary disaster. Around the same time, the Deccan traps of what is now India were releasing prodigious amounts of volcanic gases. This vast flood basalt event had already been creating environmental stress. CO2 emissions driving warming, acid rain altering soil and water chemistry, and ocean acidification destabilizing marine ecosystems. Some scientists argue that the asteroid was merely the final push in a pre-stressed world, a 1-2 punch that ensured near-total collapse. Others debate whether the Deccan volcanism or the impact alone was the primary driver, but the convergence of these two events makes clear that the end of the dinosaurs was not a simple, single cause. The consequences for terrestrial life were immediate and staggering. Giant herbivores like Alamosaurus, even at the peak of their power and numbers, could not escape a world where plants no longer grew in sufficient quantities to sustain them. Apex predators like Tyrannosaurus rex, once masters of the land, found their prey vanishing, the intricate food web unraveling in a matter of months. Smaller animals, insects and birds faced extreme thermal stress, starvation, and habitat loss. In the oceans, marine reptiles such as mosasaurs and plesiosaurs, along with ammonites and many plankton species, suffered similarly dramatic declines. Fossil evidence shows a stark, abrupt boundary layer, rich in iridium, soot, and shocked quartz, a geochemical fingerprint of catastrophe. Yet not all life perished. Certain groups survived, often because of traits that had little to do with size or dominance. Burrowing animals, small mammals, birds, and some amphibians and turtles endured, buffered by their ability to find shelter or subsist on limited resources. This pattern underscores a fundamental truth in evolution. Survival is often dictated by flexibility and adaptability rather than strength or predation skill. As paleontologist Steve Brusatte observes, the end of the non-avian dinosaurs was sudden and brutal, but it did not erase all life. Some lineages, resilient and resourceful, passed through the storm into the world that followed. The Chicxulub impact serves as both a dramatic punctuation and a philosophical mirror. For over 165 million years, dinosaurs had dominated Earth, surviving cataclysms, climate shifts, and competition. Their world was a peak of ecological stability and evolutionary experimentation. Yet in a single instant, the celestial lottery intervened, reminding all life that dominance is temporary and that even the most sophisticated adaptations offer no guarantee against random, external forces. In the aftermath, ecosystems lay in ruin, smoke and ash filling skies for months, perhaps years. Vegetation was slow to recover, herbivores struggled without adequate food, and predators starved in turn. The Earth entered a phase of ecological reset, clearing the stage for the rise of mammals and the birds, the true heirs of dinosaurian resilience. Though the non-avian dinosaurs vanished, the evolutionary momentum they had built endured in the traits passed to birds, allowing flight, feathers, and complex behaviors to persist into the modern age. Yet while the impact ended the reign of the great reptiles, it also highlighted an enduring principle of life. Extinction is rarely absolute, and resilience often emerges from the ashes. Tiny lineages, previously marginal and overshadowed by giants, can become the architects of a new world. In this sense, the Chicxulub event was both a finale and a prologue, a violent punctuation mark that closed one chapter of Earth's history while setting the stage for another. Even as the dinosaurs fell, life itself continued, stubbornly and ingeniously, proving that while extinction can reshape the world, it cannot annihilate the potential for life to adapt, evolve, and ultimately thrive. But extinction is never absolute. Even as the skies and landscapes smoldered from the aftermath of Chicxulub, not all dinosaur lineages were extinguished. Among the chaos and ecological collapse, a lineage of small, agile theropods persisted. These were the ancestors of modern birds, creatures that had spent millions of years experimenting with feathers, flight, and complex behaviors. Paleontologists now see them not as a separate, unrelated group, but as living dinosaurs, the last living threads of a vast evolutionary tapestry. Their survival reframes the story of the end Cretaceous. It was not simply about death, but about transformation. Fossil discoveries over the past few decades, particularly from the rich beds of Liaoning, China, have revealed dozens of feathered theropods. Species such as Microraptor anchiornis and Velociraptor mongoliensis show a remarkable continuity with birds in both skeletal structure and integumentary features. Feathers, once thought exclusive to avian lineages, are now known to have been widespread among Maniraptoran dinosaurs, serving roles in thermoregulation, display, and eventually flight. The arrangement of bones in the wrist, the semilunate carpal that allows wing folding, and the hollow pneumatic bones all demonstrate that the transition from ground-running predator to airborne organism was gradual, incremental, and deeply rooted in dinosaurian anatomy. John Ostrom, whose work on Deinonychus in the 1960s reignited the bird-dinosaur connection, emphasized that these creatures were not proto-birds in some hypothetical sense. They were fully integrated members of the theropod clade. Thomas Huxley, much earlier, had already argued for the structural continuity between birds and dinosaurs, but modern fossil evidence has now confirmed it unequivocally. Xu Xing and his colleagues have documented fine details of feather morphology and skeletal homology that allow us to see the survival of dinosaur traits not as vestiges, but as active evolutionary innovations carried forward into the present day. These living dinosaurs were small, lightweight, and ecologically versatile. They could hide, forage, and exploit niches that had been irrelevant to the giant forms of their ancestors. In contrast to the massive Tyrannosaurus or Alamosaurus, they relied on agility, flight, and social strategies for survival. Their feathers became instruments not just of insulation, but of survival strategy, and eventually of flight, enabling them to escape predators, colonize new habitats, and exploit food sources that had been previously inaccessible. Molecular and genetic studies have reinforced this picture. Comparisons between avian DNA and that extracted from fossilized dinosaur remains, though challenging, show remarkable conservation of developmental pathways. Genes controlling limb development, feather growth, and metabolic regulation have remained consistent across tens of millions of years. In this sense, modern birds are a living archive, an uninterrupted lineage connecting the Triassic and Jurassic hunters to the creatures that flitted through forests and plains immediately after the extinction. Yet the survival of birds is not simply about anatomy or genes, it is also about ecological opportunity. With the giant herbivores and apex predators wiped out, niches across the globe were suddenly open. Ground-dwelling birds evolved into scavengers, insectivores, and eventually into species capable of long-distance flight. Some took to aquatic environments, others specialized in seed dispersal, and yet others became apex aerial predators in their own right. The post-impact world was a laboratory for adaptive radiation, and birds were poised to inherit it. Steve Brusata has noted, what we see today in the diversity of birds is not a new invention, but the continuation of a lineage that survived the end Cretaceous apocalypse. They are living reminders that extinction is not final for all, and that evolution often rewards those that can adapt rather than those that dominate. The bird's survival teaches us that the story of the dinosaurs is not only one of colossal size and spectacular predation, but also of resilience, innovation, and transformation. In the wake of the KPG extinction, the world that once teemed with towering sauropods, armored ceratopsians, and fearsome theropods was now a fractured landscape. Forests were thin, climates were unstable, and oceans teemed with empty niches. Yet through these conditions, the small, feathered theropods persisted. They moved through the wreckage, feeding on insects, scavenging carrion, and eventually mastering the skies. Evolution had shifted the axis of survival from brute strength to flexibility, from dominance to adaptability. In time, these survivors would radiate into the incredible diversity of modern birds, filling ecological roles that the giants could never have occupied. Their wings, initially for gliding or display, became instruments of power and mobility. Their small size, once a disadvantage in a world dominated by reptiles, became a key to persistence in a world of uncertainty. The line between dinosaurs and birds had blurred entirely. The ancient predators that had once stalked the plains were now hidden in plain sight, singing in the trees and soaring through the air. This continuity reshapes our understanding of the KPG boundary. Dinosaurs did not vanish entirely. They transformed. The end of the Age of Giants was not the end of dinosaurian influence, but the beginning of a new chapter, one written in feathers and flight. The legacy of the Mesozoic, of 165 million years of experimentation and survival, endures every time a bird takes wing at dawn. And with the giants gone, something else began. The world after the KPG extinction was both empty and alive. Where once towering sauropods grazed and apex predators prowled, only scattered survivors remained. Small mammals, long living in the shadows of dinosaurs, seized the opportunity. They diversified rapidly, filling niches left vacant by giants. Rodent-like creatures became burrowers, gliders, and climbers. Primitive primates, insectivores, and carnivores explored the ecological spaces left by the vanished reptiles. Evolution, ever opportunistic, was swift. The age of mammals was beginning, but it was only possible because dinosaurs, once the ultimate rulers of the land, were gone. Yet this transition was not simply about mammals winning a contest of survival. It was about the fragility of dominance itself. Dinosaurs had ruled the Earth for 165 to 180 million years, a span longer than any other land-dwelling group. Their reign included catastrophic events, climate swings, and even localized extinctions. They were adaptable, complex, and at times socially sophisticated. And yet, all of it was insufficient against the abrupt planetary-scale changes wrought by an asteroid and volcanic fury. This is a sobering reflection. Longevity and power do not guarantee permanence. In an indifferent universe, survival is contingent, not earned. The fossil record preserves this lesson in exquisite detail. Sites like Nahuelbuto, New Mexico, show dinosaurs thriving right up until the final moments, contradicting older ideas that they were in decline before the impact. Alamosaurus roamed the floodplains. Tyrannosaurus hunted, and herds of hadrosaurs and ankylosaurs grazed peacefully, all within striking distance of annihilation. Their sudden disappearance illustrates the unpredictable nature of mass extinction. Dominance, intelligence, size, or speed, none could forestall the cosmic lottery.
From a scientific perspective, the aftermath highlights the role of ecological vacancy. With the giants gone, entire food webs collapsed and reassembled. Mammals, birds, amphibians, and surviving reptiles radiated to exploit the new opportunities. Ecosystems were rewired. Evolutionary experiments that had been constrained by dinosaurian supremacy suddenly became possible. In a sense, the Earth was reset, not destroyed. Life was resilient, but the players were not the same.
Philosophically, this challenges how we interpret our own place on the planet. Humanity, for all its technology and cognition, is subject to the same vulnerabilities. The dinosaurs ruled longer than any other terrestrial animals, yet they vanished without warning. Climate change, pandemics, asteroid impacts, and volcanic supereruptions are reminders that the planet does not negotiate. Dominance may feel like control, but it is an illusion in the vast scales of deep time. Dinosaurs also teach us about the power of transformation. Even in death, they reshaped life's trajectory. Birds carry forward traits developed over 230 million years of theropod evolution, a lineage of survival and adaptation. Mammals evolved in response to the emptied ecological landscape. The lessons of adaptability, opportunism, and contingency resonate across time. Life is not static and dominance is fleeting. It is the capacity to respond, evolve, and persist that determines which lineages endure. Their story is also one of scale and spectacle. From the gargantuan Argentinosaurus to the cunning pack-hunting Deinonychus, Dinosaurs exemplified extremes of evolution: size, speed, intelligence, and complexity. Yet none of this could shield them from sudden planetary catastrophe. In this, they are both awe-inspiring and humbling. Paleontologists like Steve Brusatte have remarked that understanding their final days teaches us about resilience, but also about limits. Dinosaurs thrived until the very end. Their extinction reminds us that even the most dominant life forms are contingent, temporary. We are left with a question that echoes through time. If the mightiest creatures ever to walk the earth could vanish in an instant, what guarantees our own survival? Humanity has reshaped the planet in ways dinosaurs never could, altering climates, redirecting rivers, extinguishing species, but this very agency carries risk. The lesson is stark. Adaptation, foresight, and humility are the only defenses against forces greater than ourselves. Dominance alone is never enough. Yet there is hope embedded in the aftermath. Life always finds a way, even after the most devastating events. Birds continue to soar, mammals continue to diversify, and ecosystems gradually rebuild. Extinction, while final for some lineages, is an opportunity for others. The Earth's story is continuous, unbroken by individual catastrophes, even those as dramatic as Chicxulub. Dinosaurs teach us that while we are transient, life itself endures, evolving through every crisis, experiment, and catastrophe. As we reflect on this ancient lineage, it is clear that dinosaurs were more than just titanic creatures of the past. They were experimenters in life, social innovators, and ecological architects. Their dominance was immense, but their legacy extends beyond their extinction. They transformed Earth, set the stage for mammalian success, and left behind descendants that still fill the skies with song and flight. Their story is a mirror showing the transience of power and the permanence of adaptation. And so, as we study the bones, the trackways, the nests, and the fossilized forests, we are reminded of our own place in the chain of life. Dinosaurs remind us that the Earth is larger than any one species, that time is indifferent, and that survival favors not the strongest or the smartest, but the most adaptable. They ruled, they thrived, and they vanished. Yet through their extinction, life's story continued, and it continues today in ways both visible and hidden. If dominance could not save them, what makes us think it will save us? If this journey through our past helped you understand what it takes to survive, subscribe to Science of Survival. We release new documentaries every week, exploring extinction, adaptation, and the fragile line that keeps humanity alive.